All right, let's do another example applying the Sylow theorems. Sylow theorem number 3, if you remember, tells us that the number of Sylow P subgroups is congruent to 1 mod P and also has to divide the size of the group. This really restricts the options that you have for the number of Sylow P subgroups. So here's an example. Let's say that the size of our group is 30, and 30 is 2 times 3 times 5. How many Sylow 3 subgroups are there? Well, the number of Sylow 3 subgroups has to be congruent to 1 mod 3. So it could be 1, 4, 7, 10, 13, 16, and so on. But it also has to divide the size of the group. And out of these numbers, the only numbers that divide 30 are 1 and 10. So the number of Sylow 3 subgroups is either 1 or 10. How many Sylow 5 subgroups are there? Well, in this case, S has to be congruent to 1 mod 5. So it could be 1, 6, 11, 16, and so on. But the only elements on this list that divide 30 are 1 and 6. So there are either 1 or 10 Sylow 3 subgroups, and there are either 1 or 6 Sylow 5 subgroups. But I claim this: there cannot be ten Sylow 3 subgroups and 6 Sylow 5 subgroups. I'll prove it, but the reasoning is if there were 10 Sylow 3 subgroups and 6 Sylow 5 subgroups, there wouldn't be 30 elements in your group. This accounts for too many elements to be a group of size 30. Why? If there are 10 Sylow 3 subgroups, 2 of these Sylow 3 subgroups could only intersect trivially. I should write that down. If there are 10 Sylow 3 subgroups, any 2 different subgroups of size 3 can only share the identity. Why is that? Well, if A, or actually maybe I should say, if H1 and H2 have size 3, then the intersection is a subgroup of H1. So I'm saying if H1 and H2 have 3 elements in it, the intersection is a subgroup of H1. And any subgroup of a group of size 3, 3 is a prime number, so any subgroup of a group of size 3 can either be just the identity or the entire group. So then this is H1 intersect H2 is either equal to just the identity element or H1. So this shows that if you take two different subgroups of size 3 or two different subgroups of any size that's a prime, their intersection can only be the identity element or the whole thing, in which case H1 is equal to H2. So if I have 10 Sylow 3 subgroups, any two of them can only intersect in the identity. This accounts for 20 elements in G of order 3. I have 10 subgroups. Each of them contains the identity, so the identity is in all of them. And each one of these 10 subgroups have two other elements in them. Both of those two elements have order 3, so then I have 20 elements of order 3. Similarly, I can apply the same kind of logic to the Sylow 5 subgroups. If there are 6 Sylow 5 subgroups, any two of those subgroups can only share the identity element. That would mean there are 6 times 4, which is 24, elements of order 5. What that means is that this can't happen. I can't have 20 elements of order 3 and 24 elements of order 5 in a group with only 30 elements. The numbers just don't add up. So that means this cannot happen. We have now shown that there cannot be 10 Sylow 3 subgroups and also 6 Sylow 5 subgroups. So what that means is on our list here, we cannot have 10 and 6. Meaning, one of these numbers, the number of Sylow 3 subgroups or the number of Sylow 5 subgroups, has to be 1. So thus, there is either one Sylow 3 subgroup or one Sylow 5 subgroup. And as remarked in our last video when we were discussing A5, if the number of Sylow subgroups, Sylow P subgroups is 1 for any P, that means your Sylow P subgroup is normal. So thus, conclusion, G has a normal subgroup. G is not simple.